Yes, thank you. Yeah, my name is Patrizio Giovannotti. I'm a PhD student at Royal Holloway University of London. I'm also a data scientist for Centrica, which is the holding company of British Gas, and which I thank for the support. And yeah, in this talk, we will be talking about paraphrase detection and how to use conformal prediction to improve it. So first of all, a few definitions. What is a paraphrase? So we are talking about natural language processing, and in general, a paraphrase can be defined as a pair of sentences, A and B, which can have different lengths, and if B is different from A, but conveys the same meaning of A, we can say that B is a paraphrase of A. So it's basically a pair of semantically equivalent sentences. An alternative definition says that if A implies B and B implies A in a logical way, then we are looking at a paraphrase. So it's a mostly bidirectional entailment. In general, the machine learning approach to tackle paraphrase detection requires the concatenation of A and B into one single sequence, which is separated by a special token, and then use that as our feature vector, and then treat the problem as a binary classification task. So a few simple examples. If A is I am hungry and B is I feel hungry, then our data example will be this sequence with a separation token that tells the algorithm that this is where the first sentence stops and the second sentence starts. And this is a positive example, of course, because these two sentences mean the same, have the same meaning. Second example, of course, is a negative one. I would like to play is different from I'm hungry. And the third example is still a negative one, because even if you're hungry, that doesn't mean that you haven't eaten all day. Well, maybe the opposite is true. So it's not bidirectional, and that would be classified as not paraphrase as well. So in general, this definition of paraphrase is it's not very rigorous. The meaning of a sentence can vary depending on how you look at it, and we need to trust our human annotators to make the correct judgment when labeling the examples. So this task is a foundational task for NLP in general. It can be used in text summarization and question answering. So in many more complex NLP tasks. Okay, so what is the state of the art for paraphrase detection? What is usually used to detect paraphrases? The transformer architecture, it's ubiquitous in NLP right now. It was introduced in 2017 by Google and was originally used for machine translation. And it performed really well. And being based on this attention mechanism, which is basically a sequence of matrix multiplications, it was really easy to scale and to parallelize. So it gained quite a lot of popularity. And another team at Google then decided to isolate the first part of the transformer, which is called encoder, and use it to build another architecture, which is called BERT. So BERT, it's built in the workflow of BERT is the following. In the pre-training phase, we take the sole encoder of a transformer, we train it on two self-supervised tasks. So guessing the missing word, for example, or predict if a given sentence can follow the previous one. So the training set for these two tasks is boundless in a sense that you can always create a new example by removing a word and use that as a label for the example. So they were able to train this encoder on on an enormous corpus of documents. And at the end of the training, the output of the transformer would be bidirectional encoder representations. So that's when where the name BERT comes from. And the nice thing about BERT, so once you get this pre-trained model, the nice thing is then you can use the pre-trained model to against many other NLP tasks or downstream tasks. So traditionally in NLP, you would have to build a different pipeline depending on the task you wanted to solve. So one for paraphrase detection, one for sentiment analysis, and so on. While with BERT, you can just use the pre-trained model and just replace the last layer and then retrain it on the dataset of your choice, and you would get pretty good results. So yeah, it was definitely a step forward in terms of portability of models. And this is exactly what we did. So we took a pre-trained model and fine-tuned it on a paraphrase detection dataset. Yeah, this is just a graphical depiction. We get our 2 sentences as input, and after a bunch of matrix multiplications and feed-forward layers, we can get some encodings and an encoding for the class, which could be either 0 or 1. This is the token we will be using for classification. Yeah, so in general, BERT is just one of many more transformer-based models. Some of them are better at language generation, like decoders. Some are better at machine translation or forecasting, like the sequence-to-sequence one. And 1 month ago, the entire department of Stanford, of AI in Stanford, coined this new name, foundation models, for all this class of pre-trained models. This sparked some discussion in the community because people say, you know, why do you call it foundation if we don't really know how do they work in practice? Or in theory at least. So yeah, we'll see if this new name will gain traction. But anyway, in this 160-page long report, some of the key requirements, especially around AI safety, were about uncertainty quantification and robustness to distribution shifts. So, okay, let's see how BERT does in terms of uncertainty estimation. So we know that a fine-tuned BERT model produces a logit, Z, which is a real number for each label. And usually we get the label corresponding to the highest logit or logit, and we take that as the point prediction. But logits can take any real value. So they're not a good measure of uncertainty. So this is why usually they're passed through a softmax function to get scores in the interval 0, 1. And now the output resembles a probability distribution. But still, these scores are not representative of the empirical error rate. So there's no guarantee that if I get a 0.8 softmax score, I am right 80% of the times. So in general, transformer-based models can be poorly calibrated, and they're not reliable when in terms of uncertainty. So yeah, our contribution then is to present a method of reliable uncertainty estimation for transformer-based models, which is based on conformal prediction, and apply it to the paraphrase detection task and show the results for several variants of predictors, and also introducing a simple nonconformity measure, which is based on the raw output, so on the logit of the transformer. It doesn't rely on the softmax function or logistic function. So speaking of nonconformity measure, we will consider 2 different nonconformity measures. So for a calibration example I, if we get logit Z and softmax S scores, and the hat symbol is representative of the true label, then our nonconformity measure is just the negated value. So the nonconformity measure we're presenting is the negated value of that logit. It's a very simple one. And we will compare this nonconformity measure with the one introduced by Maltoduglu and others last year, which is based on softmax. So this is L infinite norm of the difference between the softmax for the true label and the other labels. So, and we will see if this simpler version performs better or worse or the same. Yeah, so the dataset we will be using is the Microsoft Research Paraphrase Corpus. It's around 6,000 sentence pairs, A/B, extracted from news websites, and they were manually labeled. as 1 if they're semantically equivalent, else 0. And there's already a default split train validation test set that we kept so that we could at least compare our results to the other papers that use the same dataset. It's a fairly common dataset. It's pretty old too. We note about the data that the label distribution is imbalanced. So there's many more positive examples than negative examples. And also that A and B are very likely to present high overlap. So on average, 70% of the words are shared between the two sentences. So like the normal example in our data set is a positive example with high overlap. Yeah, so our training setup, we are using the base version of BERT, and we will also further split the training set into a proper train, 90% of the training set, and we'll set apart 10% for calibration. And then the fine-tuning, so we will fine-tune BERT on the proper training set for 2 epochs and select the model that scores best on the validation split. And once we get a good model, then we build inductive and cross-conformal predictor and their Mondrian versions. So we will be dealing with 4 predictions for each of the 2 nonconformity measures. So we'll have like 8 models. And yeah, we also need to note that BERT's performance can vary a lot depending on the data set. And MRPC is a pretty unstable data set for BERT. Depending on the random seed, on the initial seed, you get really different results. So we decided to report the averaged value, the averaged performance scores over 5 runs. So how will we be evaluating our models? In terms of predictive accuracy, we will be calculating the macro F1 score of the forced prediction. So a forced prediction is a point prediction that corresponds to the label with the highest p-value. So it's a way to, yeah, forget about the prediction set and just take one. In this way, we can at least calculate an F1 score and compare it with the base BERT model. Then we will also look at the validity of our models and the efficiency, these 3 criteria that will be defined in a second, and also look at the credibility scores of our test examples. Yeah, so the macro F1 score is simply the arithmetic mean of the F1 scores over all the labels. So we calculate the F1 score for each of the labels and we just average the values. And this is a good choice for unbalanced data set. Whereas if we were choosing a micro F1 score or a weighted F1 score, we could end up with a system that is more rewarded for recognizing the majority class, which it's not what we want. We want our predictor to be good at both classes. So we are using macro F1 score for that. For efficiency, we have S criterion, which is the average p-value over all test examples, and the OF criterion, which is also called average false p-value. So where we only count the p-values corresponding to the false labels. Both these values need to be possibly low or small. So the smaller the better. And criterion instead measures the average size of the prediction sets at different significance levels. So for each significance level epsilon, we can calculate what's the average prediction set size and see how it varies and how quickly it grows towards 1. Okay, so let's have a look at our results. This is the standard ICP conformal predictor, inductive. We can see that the validity is confirmed. So we are able to control the error rate based on the significance level. If we get 0.3 significance, we get 0.3 error rate, which is nice. However, we can also see that the error rate for the single classes, so the so-called conditional validity is not doesn't hold as expected. So higher errors for the zero class, for the negative class, are compensated by smaller errors for the positive class. So with the Mondrian version, instead, we can see that conditional validity is achieved. So we still get a valid model, but we also get a validity for both classes. And this looks the same, more or less, for the cross-conformal predictors as well, where, yeah, the lines are a bit smoother because, of course, we are averaging over 10 different folds, and maybe less striped, but yeah, we could say that the validity is achieved in this case as well. Let's have a look at the predictive performance. So first column of this table, we are looking at MACREF score. So that's the predictive accuracy. BERT original model trained on 100% training set, score 77. So first of all, we can see that all our models perform basically the same as BERT. So there's no loss in predictive accuracy, which is nice, considering that we are training on 90% of the, so on less data. And yeah, cross-conformal predictors, they score even better than BERT for both the non-conformity measures. That's probably because we are doing basically cross-validation. So yeah, probably it yields better results than the normal BERT model. In terms of efficiency, we can see the S and OF scores. Usually Mondrian predictors are always, not usually, actually always, Mondrian conformal predictors are less efficient than their standard counterpart. That's, I think, is the price to pay for the conditional validity. So they're always kind of like 1 point less efficient. And another thing we can see from the table is that there's not a lot of difference between the two non-conformity measures. So we can see that, you know, I am highlighting here the best values, the best scores, and they're all in the softmax. They're all belonging to the softmax function. But if you look at the values, we can see that there's no significant difference. We are talking about 1,000 difference between the scores. So we can see that our simpler non-conformity measure performs more or less the same as the softmax version. Look at the prediction set as well. So at 0 significance, so when we want to have 100% confidence, of course, we always get both labels, 0 and 1 output. Yeah, here, yeah, I'm just displaying from the 0.2 and less. And yeah, even here we can see that the non-Mondrian predictors, so the blue and the red one, are always, they output smaller prediction sets basically all the time, and the yellow and the green one, which are the Mondrian versions as well, they're always a bit more, bit less efficient. And that's also valid for the cross-conformal setting, even if maybe less evident. Lastly, we wanted to look at the credibility scores for the test examples. So credibility is defined as the largest p-value in a prediction set. And usually if this value is high, then the example is highly conformal to the training set. So it's normal in a sense. While with low credibility, we are probably looking at an anomalous example. So it's either maybe a new label that we didn't know about, or maybe the example is not IID. So credibility tells us something about the data distribution, the training data distribution. So can we use it to discover properties of the data? So like what is normal, what is strange in the data set? So I had a look at some low credibility examples, and let's see this example here. So while waiting for a bomb squad to arrive, the bomb exploded, killing whales. And the bomb exploded while authorities waited for bomb squad to arrive. So these two sentences are pretty similar, yet they are labeled, the true label is negative. So it's not a paraphrase, probably because there's no mention of this man that was killed by the bomb here. So it's not bidirectional. But yet there's a high overlap of words. Almost all the words are the same. And our model predicts paraphrase, but with low credibility. And the opposite, it's true for this other example here. So here we have Mrs. Clinton said she was incredulous that he would endanger the marriage and family. Here we have she hadn't believed he would jeopardize their marriage and family. So here the meaning is the same. In fact, the true label is positive, but the words are fairly different. So there's no Clinton, there's no incredulous, there's no endanger, it's changed with jeopardized. So in a sense, this is a negative example, is a strange positive example, given that so few words are in common. And this has low credibility as well. This we could notice this in many test examples. So we came up with a claim that our model actually sees word overlap as supporting evidence for positive examples. So in a sense, we thought that maybe BERT is not really that intelligent. Maybe it's just looking at the overlap of the words and trying to see if there's a lot of overlap, then the example is positive. So we decided to plot the credibility scores of the test examples against the percentage of overlap. And here we can see that actually for the positive label, the higher the overlap and the higher the example is conformal to the training set. And that makes sense because we actually knew that the majority of examples were positive. So this is for the positive label and with a lot of overlap. This is not true for the negative label. Actually, there's no relationship between overlap and credibility. We can't infer anything. And usually the credibility scores are actually fairly low. So it's as if negative examples are never representative of the training set. And that also makes sense because there's more positive examples than negative in the training set. So we wonder what if we use the Mondrian conformal predictor then that should be more sensitive to less popular labels. And when we use the Mondrian conformal predictor, we see that we still have a positive relationship between overlap and credibility, but we also get this negative association between credibility and overlap. So basically here we can see that the lower the overlap, the more credible a negative example is. So the Mondrian predictor tells us something about the data distribution that we knew because we actually analyzed the dataset before, but yeah, by using credibility, we could infer some properties of the data. So in conclusion, we presented a method to enrich transformer-based models with uncertainty estimation, which is based on conformal prediction, and we shown results on a paraphrase detection task. We introduced a simple nonconformity measure based on logits that performs as well as more complex nonconformity measures. So we obtained a valid predictor with no loss in predictive accuracy. And we also studied the correlation between credibility and data features as a plus. For future work, of course, we would like to try with larger and modern data sets. There's many more paraphrase detection data sets out there. Extend these experiments to other NLP tasks, like maybe sentiment analysis or text classification in general. Also experiment with different pre-trained or foundation models that may be better than BERT in predictive accuracy and so on. So thank you very much for the attention.